Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. Variations of this experiment spurred public debates between Albert Einstein and Niels Bohr on the true nature of reality. It's been called the granddaddy of all quantum weirdness. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
QuantumLaserPointers.com.
I grew up in a small town in New Jersey called Highland Park. My father, when I was young, owned a small grocery store, and later that burned down, and he opened a dry cleaners instead. Neither of my parents went to college. I have two sisters. All of us kids did go to college. As far as I can remember, there was no background of science in my family. But I did get interested in science somehow when I was very young, I think partly through television. One thing which I remember was an excellent program that was on when I was a kid called Watch Mr. Wizard, which was on for many, many years. And it was incredibly good, I thought. And that's probably what initially hooked me really on science. While I was in grade school, I think I knew I wanted to be a scientist. I don't think I understood that there were different kinds of scientists yet. When I got interested in science, I think actually my family was very happy about it. They did not know the difference between science and engineering. I think they really thought I was interested in engineering, and that's practical and good, and you can get a good job. So they liked the idea. And I think only gradually later they realized that there was a difference maybe between science and engineering, but by then it was too late. A good teacher really can be incredibly influential on a young person, and in my case, I think I was strongly influenced by a fabulous high school physics teacher. His name was Robert Landrum. He was unbelievably dynamic and unbelievably excited about physics. In truth, it was clear even then, and more clear now, that he didn't actually know that much physics. But you don't necessarily have to know that much physics to get across the enthusiasm for it. And he, in fact, I was very lucky, actually. There were a number of other students in my class who were very interested in math and science and things like that. One event which I remember well, which I think had a lot to do with exciting me about physics, and maybe in particular theoretical physics, was when I was in high school. And a friend of mine was doing a sort of an after-school project, an experiment. The experiment was that he took a yardstick and drilled holes in different places, and then pivoted the yardstick about each one of those holes and let it rock back and forth and time the period as a function of where the hole was in the yardstick. And he was drawing these graphs and having lots of fun doing that. At this point, I had just learned enough about Newtonian mechanics and a little bit of calculus, so I was able to go home one day and ask myself, could I figure out what the answer should be according to Newtonian mechanics? And it was really at the limits of what I could do, but I was able to do it. And I came back with an equation for what the period should be. And then we took my equation and my friend's data, and back in those days you used slide rules to figure out numbers that weren't any calculators. We took out a slide rule and figured out what the number should be according to my formula and plotted it against his data. And it fit beautifully. It actually worked. I'm not sure why it worked so well, because you think there must have been some friction, which I'm sure I did not take into account. But nonetheless, it did work very, very well. And I was enthralled at the idea that you could figure out by pure thought how a mechanical system like this should actually function. And it really sort of blew my mind that you can go home and calculate something, and it really does predict what the real world will do. I'm one of those people who married his high school sweetheart. So my wife and I started dating, I guess, when we were in 9th grade or something like that. We certainly both dated other people before we finally got married. We got married just before I got my PhD. and we've been happily married ever since. We have 2 children. My son has gone into mathematics, and math and physics are pretty closely related. Certainly, physicists need and use a good deal of math. And in fact, I've had many very, very helpful conversations with my son. I usually don't understand completely what he's doing, but I can tell him what I'm doing. And he has certainly made a number of very significant suggestions about how to get through some of the mathematical aspects of my work. And I've acknowledged him in several of my papers, and other physicists have even acknowledged him in papers, because we talk around. And it's cute, actually. There's a physicist who we've had contact with, Lenny Susskind at Stanford, who refers to a particular piece of mathematics as the son of Guth theorem, because he learned it from my son Larry. I went to college at MIT. MIT then, and probably now, has a somewhat unusual student culture. It was certainly very different from my high school. In my high school, there was a very clear hierarchy of social life, who was in and who was out. At MIT, nobody cared who was in and who was out. It really was, for the most part, a class of 1,000 people, each of them doing their own thing. And I think that's just great. I think that's really the way life should be. And at first, I think a lot of people, including me, had difficulty because of the fact that the group was so talented. I, for example, in high school was the best broad jumper in my class. And I assumed that when I went to an egghead place like MIT, I would certainly be the best broad jumper in my class at MIT. Turned out there was a guy from Africa who could jump about 3 feet further than I could. I was completely out of it, nowhere near the competitive level. But what happened gradually, both for me and I think for most of the 1,000 of us classmates, is that we gradually discovered that there were so many different niches that everybody got to do something that he really felt that he was good at and one of the best. Most of us, those of us who were lucky, found something that we really liked and that we could run with. And I think it was during college that I realized I wanted to be a theoretical physicist. I think it was at that point I realized there was a distinction between being an experimental physicist and being a theoretical physicist. And I always liked math, which is part of the technique that you need to be a theoretical physicist. And I always liked the idea of attempting to understand how nature behaves at the deepest possible level. And I think the natural field to pursue that goal is theoretical physics. I stayed at MIT for graduate school and decided I wanted to specialize in particle theory, which I think is the natural sort of thing to go into for somebody like me who really felt that the ultimate goal was to understand the fundamental laws of nature. That's really what particle theory is about. I worked in particle theory for 9 years or so before I got involved in cosmology. And these were various postdocs, first at Princeton, then Columbia, and then Cornell. It was while I was at Cornell that I got drawn into cosmology. And it was really the work of a friend of mine entirely. Wasn't really my own volition at all. A friend of mine came to me one day. He got interested in a new class of particle theories called grand unified theories. And in particular, he was interested in a peculiar kind of a particle called a magnetic monopole. And it turned out that these magnetic monopoles were so heavy that you could never imagine producing them in a particle physics accelerator experiment. So the only access that one would have to them is to think about whether or not they could have been produced in the early universe. And my friend dragged me into thinking about this question, and I got fascinated in cosmology, and I've really been working in cosmology ever since. Cosmology is basically the study of the universe as a whole, and for the most part it means studying the early history of the universe. At least that's certainly the part of cosmology that I've worked on. And it's kind of a detective story. The idea is to take the clues that we have about what the universe looks like today and try to extrapolate backwards and figure out what the universe looked like at earlier times and how all this started. One big step happened, maybe during the middle of the 20th century, when people worked out the basics of the Big Bang. The Big Bang theory being the theory that the universe started out incredibly small and has been rapidly expanding ever since. In order to make that theory work, the initial expansion rate couldn't be any old thing. It actually had to be very precisely tuned to a number that was related to the mass density at the time. The fine-tuning that was needed was really very extraordinary. If you looked at the universe at 1 second after we think it began, the expansion rate had to be fine-tuned to about 15 decimal places to make the theory work, to make the universe end up looking anything like what we see. And nobody had any idea how it got tuned, what it was that drove the universe to have exactly this expansion rate. And you had to assume that to make the Big Bang theory work. Another mystery, which I was actually not aware of at all until later, but another important mystery is that people didn't understand what it was that made the universe so uniform. If the universe really started out in a sudden bang, it would have, according to calculation, have separated so quickly that the different pieces flying off in different directions would not have had any contact with each other at all, even if they tried to communicate at the speed of light. Yet somehow when we look around the universe today, what we see is that the universe looks incredibly uniform in all directions. The cosmic background radiation, which we think of as the afterglow of the heat of the Big Bang explosion itself, is known to be uniform in all directions to an accuracy of 1 part in 100,000. Unbelievably uniform. And we didn't understand at all how it would get that way from a simple explosion. It turned out, however, when I was working on a totally different problem, I was working on the problem of understanding why we didn't see the magnetic monopole. In the course of trying to understand that problem, I came across this idea called cosmic inflation, which is a twist on the conventional Big Bang theory. It inserts into the Big Bang sequence of events a period, a very short period, of extremely rapid expansion driven by a peculiar form of gravity, which, according to Einstein's general relativity, is possible, a peculiar form of gravity that actually acts repulsively and provides what really is, in the context of this theory, the bang of the Big Bang. It's this repulsive gravity that causes the incredibly rapid expansion of the Big Bang explosion. This incredibly rapid expansion answers both of those questions. It drives the expansion, and it turns out it drives it at just the right rate that had been needed, but not explained in the conventional Big Bang theory. And also, because it's actually creating matter as it expands, it arranges for that matter to be uniform. So the uniformity of the universe also gets explained. The theory also has the rather spectacular consequence that it actually explains the origin of essentially all of the matter in the universe. I have to qualify it by saying essentially, because you have to start with about 1 gram of matter or so to get this going. So it's not really the ultimate theory of how the universe began, but it does explain how the universe went from being about 1 gram of mass to being the fantastic amount of matter that we see in the universe today. The work that I've been involved in is an incredible leap, and I can't say that we know for sure that we're right, but we have very detailed theories which make real predictions, and those real predictions do agree very well with what actually is observed by astronomers as properties of the universe today. Once I came across these ideas, I was very nervous about it because it seemed very dramatic, and most very dramatic ideas end up being wrong, or else somebody would have found them already. And I was very puzzled if it was right, how come nobody found it already? But I spoke to people about it, and nobody seemed to notice anything wrong with it. I then started giving talks about it. The first talk I gave about it was at SLAC, the Stanford Linear Accelerator Center, where I was working at the time. And that talk for me, was a big boost of morale because there are a lot of very good physicists in the audience. None of them noticed anything wrong with it. And some of them got very excited about it and started telling their friends. And it was really the beginning of a wave of excitement. The present time has been called by many people the golden age of cosmology, and I think the word really is valid. When I was in graduate school, which to me doesn't seem that long ago, almost nothing was known about cosmology. The cosmic background radiation was discovered just before I started graduate school. Nobody knew much about it, and really there have been very few measurements of it, and there really was very little information about it. One of the big questions when I started working on cosmology was to understand the non-uniformities of the early universe, the small ripples on an almost uniform background. And we were working very hard to calculate them. When we were working on it, I'm sure I was absolutely convinced that nobody would ever be able to see them because they're just too faint. Now we have incredibly precise measurements of these non-uniformities in the cosmic background radiation, the variations in the temperature from one direction to another. We have a fantastic wealth of information now and very detailed models of how the universe worked. The amount of information is just unbelievably different from what it was. So it's a very exciting field. There's still many huge mysteries. It's a field that's amazing, really, both for how much we know and for how much we don't know. We don't know, for example, what most of the universe is made out of. 70% of the universe is mysterious stuff called dark energy. Another 25% is mysterious stuff called dark matter. Dark matter and dark energy actually are different things, and together they make up about 95% of the universe. Only about 5% is made out of stuff that we really understand, stuff made out of protons and neutrons and electrons, like the material that we're actually made out of. So there are big mysteries. Since this theory called inflation is not really a theory of the ultimate beginning, obviously one does want to try to think about the ultimate beginning. But, of course, as you might guess, we don't actually know the answer. The kind of speculation that people have had have more or less revolved around the idea that the universe originated from some state that might be called absolute nothingness, where absolute nothingness is usually thought of as being not only the absence of matter, but also even the absence of space and even the absence of time, and that somehow the universe materialized through some kind of a quantum transition from this state of absolute nothingness. And speculating about this, one has to assume that the laws of physics can exist even if the universe doesn't. And we have no idea. People don't even speculate about where the laws of physics came from. We just do our best to understand what the laws of physics are. I've never found it useful to believe in an omniscient or omnipotent God who controls things. As far as using a deistic idea to explain the universe, I always found it somewhat pointless because it only pushes the question one step backwards. Instead of trying to explain the universe, you have to explain the deity that you're inventing to create the universe. So I think we really need to grapple with the questions of what the universe is and how it originated on physical terms. And that's what I've been spending most of my adult life trying to do. I have two sisters. All of us kids did go to college. As far as I can remember, there was no background of science in my family, but I did get interested in science somehow when I was very young, I think partly through television. One thing which I remember was an excellent program that was on when I was a kid called Watch Mr. Wizard, which was on for many, many years, and it was incredibly good, I thought. And that's probably what initially hooked me really on science. While I was in grade school, I'm a young person, and in my case, I think I was strongly influenced by a fabulous high school physics teacher. His name was Robert Landrum. He was unbelievably dynamic and unbelievably excited about physics. In truth, it was clear even then, and more clear now, that he didn't actually know that much physics. But you don't necessarily have to know that much physics to get across the enthusiasm for it. And he, in fact, I was very lucky, actually. There were a number of other students in my class who were very interested in math and science and things like that. One event which I grew up in a small town in New Jersey called Highland Park. My father, when I was young, owned a small grocery store, and later that burned down, and he opened a dry cleaners instead. Neither of my parents went to college.
Quantum laser pointers brings you the infamous double-slit experiment right in the palm of your hand. Variations of this experiment spurred public debates between Albert Einstein and Niels Bohr on the true nature of reality. It's been called the granddaddy of all quantum weirdness. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
QuantumLaserPointers.com.
I think I knew I wanted to be a scientist. I don't think I understood that there were different kinds of scientists yet. When I got interested in science, I think actually my family was very happy about it. They did not know the difference between science and engineering. I think they really thought I was interested in engineering, and that's practical and good, and you can get a good job. So they liked the idea. And I think only gradually later they realized that there was a difference maybe between science and engineering, but by then it was too late. A good teacher really can be incredibly influential on